and had many top-tier publications. So today, Dr. Oncel will have the topic about advancing the frontier of on-device AI. Let's welcome our speakers. Thank you.
Thank you, Shuai, for kind introduction. Good morning, everyone. I'm Tuzel. Today, I'll share some of our recent research at Apple on efficient vision language models and also emerging directions for building more efficient foundation models. When people think about AI progress, they often think about scaling. Scaling model parameters, dataset size, tasks, and test time scaling repeatedly unlocked impressive capabilities such as complex reasoning, multimodal and multilingual understanding, code generation, AI agents. However, capability alone is not enough. The impact of AI depends on how broadly we can deploy these systems, and efficient machine learning makes advanced AI accessible to more people, more devices, more regions around the world by reducing the computational bottlenecks. Let's start by defining what we mean by efficient machine learning. At a high level, there is always a trade-off between model quality and resources that we use to either train or deploy this model. In this figure, the x-axis represents the cost, which can include training costs, such as GPU hours or dataset size, or it could be the inference cost, that could be the latency, power, memory, parameters, and etc. And as we spend more and more resources, we can achieve higher and higher accuracies. However, not all methods and models are equally efficient. The goal of efficient machine learning is twofold. First of all, we want to understand the trade-offs that are involved in this process, and then we want to push the Pareto frontier by developing better algorithms for learning and deployment. We can evaluate the efficiency of machine learning models twofold again. So we can fix a target resources that we are going to be using either for training or deployment, and we can look at the accuracy of the models. Or alternatively, we can set a target accuracy, and we can see how much resources do we need to reach to those accuracy. So throughout the talk, I'm going to be talking about these trade-offs, show curves like this, and I'm going to be touching base on both inference and the training aspects of efficiency. Today, I will review some of our recent work on efficient vision language models. First of all, Mobile Clip. It's a family of vision language embedding models. Then I will talk about FastVLM, a family of efficient vision language models for efficient deployment. Finally, I will present a new approach for disentangling knowledge and reasoning in LLMs towards a much improved efficiency. Let's start with Mobile Clip. A quick recap on CLIP, or contrastive language image pre-training. CLIP learns a shared image and text representation by training two encoders. One of them is an image encoder, the other one is a text encoder. And these encoders map the given image and text into a higher dimensional embedding space. The goal of CLIP is to map the matching pairs into a location that are nearby, whereas okay. The objective of CLIP is actually matching image and text pairs, mapping them to a nearby location, and non-matching samples, pushing them away from these points. CLIP has several applications, for example, zero-shot image classification or image text retrieval. But another major use case of CLIP is that it can be used as a predominant pre-training strategy for other models, such as vision language models. Okay, let's talk about the runtime efficiency. And for the mobile CLIP image encoder, we use a variant of the FastVLM model that we have developed in 2023. This is a hybrid transformer and convolutional architecture. We know that VITs have demonstrated remarkable success and scale effectively with data. but they do not inherently encode latency, locality and translation equivariance biases encoded in convolutional neural networks. These inductive biases are actually pretty important, particularly when we don't have too many parameters in our network. Another trade-off that we have observed is that having deeper models that are narrower actually provides a much better efficiency trade-off. However, training these deeper models when there are particularly less parameters is actually pretty difficult. That's why we use a trick that is called reparameterization. Essentially, we over-parameterize our models during training by introducing additional skip connections or parallel branches. These are though, or batch norms, additional batch norms, but these are all linear operators. So during deployment, we can collapse all these operations and then have a very efficient and small network. As I said, our model is a hybrid architecture, and it's a quite deep architecture that starts with a convolutional backbone and followed by some attentions. And almost at every stage, actually, we use this reparameterization to train more efficient models. As you see in inference, we have much less parameters. Okay, now let's take a look at the text encoder. We use a similar trick, actually. We use a hybrid model, which is a combination of convolutional layers plus some attention layers. And our convolutional layers are, again, reparameterizable. And during inference, we have much less parameters. And here is the architecture of our hybrid text encoder architecture. Now, let's talk about learning efficiency. The first ingredient for training a good model is a high-quality data set. And for training our mobile clip family of models, we use the DataComp dataset that's been introduced in 2023. This dataset contains high-quality web-crawled image-text pairs, and there are more than 12 billion image-text pairs. And for the later family of models, we use the data filtering networks variant of this dataset that filters high-quality images and text from this dataset. And in addition to that, we also introduced a new dataset called TIC-CLIP for continual training of CLIP models. Okay, so we start with a good dataset, but how can we further improve the utility of the training dataset and training? We use a technique called dataset reinforcement that we introduced in 2023. The idea is we start from an original dataset that gives us certain training efficiency. Then we do a one-time process and augment this dataset with additional information. So this could be something like maybe some information that we compute from some teacher models, certain augmentations, certain curriculums, and we can bake them into the dataset. This is a one-time operation. It takes some cost, but this is amortized through many different training jobs that we do afterwards. And the idea is when we train with this dataset, we have a much better model. How do we do it for multi-model? So this is something new that we have developed. So for multi-model image and text datasets, we introduced 3 types of additional information. The first one is actually synthetic captions. Synthetic captions are much less specific, but they are better aligned with images. So they are important for retrieval, whereas the original image captions are a lot more specific and they're important for classification. So we fuse these two. We introduce a lot of strong image augmentations. And in addition to that, we obtain a set of very strong clip teachers in an offline stage, and then ensemble these models and use the ensembled embeddings as part of our training dataset. So this is a one-time operation that augments a certain amount of information. And training with this dataset is essentially equivalent to doing an offline distillation using this clip teachers plus the captioning models and our original datasets. Training with this dataset is quite simple. So we just change the dataset and change our loss function. It is as efficient as using the original DataComp DR datasets. And what you see in here is that the orange curve shows the training curve corresponding to the original dataset, whereas the blue curves correspond to the training curves corresponding to the dataset reinforced dataset. And we see that we can train the same models 10 times faster using this new dataset. And we can also train using 100 times less data to reach the same accuracy. We released 2 variants of this dataset. The first one is a 12 million size example, and that we use for explorations such as architecture search. This actually using just this 12 million examples, you can train a clip model to have zero-shot accuracy of 62% on a single node within a day. The second data set is a 1 billion variant, and this is useful in our scaling experiments. What you see in here is, again, the orange curve shows the accuracy of the original data comp data set, whereas the blue curve, training with our new introduced data set, is actually much better. In fact, this is actually training a VIT detector across all the data sets that are introduced in the community, and this data comp TR is actually the best one. Let's take a look at the runtime efficiency of the models. For this one, we train our mobile clip models using the introduced data comp TR dataset. And what we observe is that the introduced dataset is 2.3 times have less latency compared to the CGLIP model and 2 times smaller than that. And during the time of publication, it was actually better than any of the, had the better trade-off than any of the existing models. Okay, we have released the code model and dataset corresponding to this paper, and we also have an iPhone application that you can download. Our mobile clip model runs over 100 frames per second on an iPhone 12, as you see in this image. More recently, we have improved this model to have the mobile clip 2. In this new model, we are using the improved data filtering networks dataset. And in addition to that, we have a better set of teacher models and better captioning models. And we also introduced a better architecture. And the result of this thing is actually we can have a 2 times smaller model, but or 2 times faster model with the same accuracy. Let's now move to FastVLM. In particular, I will discuss the trade-offs between image resolution, vision backbone design, and overall model quality for vision language models. Again, a very quick recap. We use a pretty standard VLM architecture where the model receives both an image and a text prompt. The image is processed by a vision encoder to compute the vision tokens. The text is processed with a text encoder. And then the processed text and images are fed into a vision language model, which is an autoregressive model, which decodes the response to the given prompt. Let's take a look at an example. In here, we ask a question to the model: how many vases in the photo contain more than one flower? On the left, we have a low resolution image. And when we feed this image to this model, it says 0. Whereas when we provide the high resolution image correctly, it classifies them actually as 2 as the response. Our observation is that image resolution is a critical determining factor, and we should be really feeding highest resolution images as possible to have really good accuracy. The challenge is that, of course, this comes with a very significant cost. So in here, we measure the cost of VLM by the time to first token, and it is the sum of vision encoders latency to construct these vision tokens, followed by LLM's pre-filling latency, which is the time that LLM processes the vision tokens plus the text tokens. Now let's take a look at how does the latency changes when we change the image resolution. Actually, the cost is even higher than quadratic in this case because of certain introduced bottlenecks after certain image resolution. And one of our goals is to build a vision encoder that can process high resolution images and provide few but high quality image tokens to be processed by LLM efficiently. To study the vision encoders effectively, we baked this experimental setup where training data, training recipe, language models are all fixed. We just changed the vision encoder and the pre-training algorithm used for the vision encoder. We evaluated popular vision backbones that are trained with high quality data, such as VITL or CGLIP models that are shown in this figure. And in addition to that, we evaluated some convolutional backbones, the one that is shown in blue. But what we have observed is that FastVIT encoders that I have described at the first part of the presentation, together with the mobile clip pre-training, actually gives us a very favorable trade-off between the time to first token and the model accuracy. That's why we use actually the backbone that's been trained that I explained just before. One problem is that this backbone is a little bit small it's been used for clip training. And what we do in here is that we actually, if you look at some of the numbers, it's 8 times smaller and 20 times faster compared to the VITR backbone. This backbone is a little bit small, so that's why we scale this model up to a FastFit HD model that processes very high resolution images. But it has more parameters, but it also at the same time produces 4 times less tokens. That's why processing with this model is actually much faster. Let's take a look at the backbone in action. In here, on the x-axis, we show the time to first token in log scale. So a very small change actually on the x-axis leads to very big differences in terms of latency. So as I said before, as we scale the size of the image, the accuracy of the models become better. This is the FastVIT. But at some point, it's actually better to change the decoder size. Initially, we start with 0.5 billion parameter decoder. Now, at some point, it's better to switch to 1.5 billion parameter model. And likewise, at some point, it's better to use a 7 million parameter model. Now, what we can do is that we can take a look at the efficient frontier of these curves. And now we can compare it with the FastFit HD model, which we can actually obtain the same efficient frontier. When we compare these two models, we observe that FastFit HD is actually 3 times faster compared to original FastFit, and at the same time, it provides 4 times less tokens. Another line of actually improving the efficiency is token reduction schemes. And there have been very successful methods in the community towards reducing the tokens by token merging or using certain other sparse priors. What we have observed is that we can use this FastFit HD backbone and just change the image scale, and we can have a pretty favorable trade-off. Here is the final results comparing the accuracy of FastVLM, efficiency trade-off of FastVLM with other models in the community. Again, the y-axis in here is the time to first token in log scale. As you can see, during the time of the publication, it provided very favorable trade-off curves compared to all the existing techniques in the community. Here, we again released all the code models and the demo of the model, and you can go to that link and then download. You can see that this model has pretty good results, both in text-rich model evaluation or captioning or other visual question answering tasks. You can also find the demo of this model in Hugging Face. Our colleagues at Hugging Face actually build a demo. You can upload your video, and at real time, it's going to produce a captioning of the video that's been uploaded. Okay, in the interest of time, I'm going to move a bit faster. We have now covered our recent work on efficient vision language models. Next, I would like to shift gears to discuss a different direction to improve efficiency. Essentially, we will look at separating knowledge from reasoning in foundation models. Even though our community has made remarkable progress in efficient machine learning, still we have a substantial gap between the server-side models and the models that we can deploy on device. And bridging this gap might not be so easy, so it might require thinking some of the core assumptions and the models that we are building in today's foundation models. Particularly, we think that how knowledge is represented is something that we need to change to do this. Let me give a motivating example. We take Quant3 2 billion parameter model. This is a relatively small size model. And when we prompt this model, we observe that this model has memorized the fact that Albert Einstein was born on March 14, 1879. So this is super cool. But at the same time, we ask the question, is this necessary? One consequence of memorizing this kind of fact in the parameters is that every time I ask a query to this model, these parameters that correspond to Einstein's birthday are loaded into memory and used in computation to answer these irrelevant queries. And how many times actually we ask a question about Einstein's birthday to these models? So ideally, we should be able to utilize this capacity for common sense and reasoning and do much better on device for general purposes. And we can separate actually this memory into certain other external storage. There are other reasons why we would like to make memories explicit. One of them is actually the privacy aspect. These models are trained with a lot of data from the web, and there's a lot of private information. And oftentimes we need to actually go back to the model and then erase this information from these models because we don't want them to be available to everybody. But this is a very difficult task actually because there is no one-to-one correspondence, and by doing so, we lose a lot of accuracy. Another reason is that the current LLM designs are monolithic. So this is quite different from how other systems are being developed and deployed. Usually software systems accesses a lot of different knowledge and data, but they're all guarded by some access control. Whereas when we learn LLMs, all the information is in the stored in the model weights and everybody has access to that. Oftentimes, we have public information or my personal information. I would like this information to be available to me, but not to other people. So a better design could be actually separating these knowledge from the parameters of the network. And finally, another reason is actually word knowledge is changing very rapidly. And to keep up to date, we need to update our models very frequently. And it might be much easier if we have an explicit form of memories. Here is our current design, which shows the behavior of the model in runtime. Given a query which fetch a set of memories from a hierarchical memory bank, and this memory bank, the retrieved memories are attached to our anchor model, and then we use this anchor model to answer this query. Let's take a look a little bit more in detail. On the upper right, we show the model. The monolithic model is shown in purple, whereas our model has this purple nodes and the green nodes. Green nodes are the retrieved parameters, and the large green part is actually the memory side. And in general, the model has a certain number of parameters. The retrieved memories are only a fraction of the model size, whereas the memory bank is actually quite larger than the original model. How do we train these models? We use a DataComp-LM dataset that was introduced recently. This contains 3 billion documents and approximately 4 trillion tokens. And we use sentence word to obtain embeddings corresponding to each document. And in an offline stage, we cluster the entire web corpus. Essentially, initially, we have 16 clusters that are further clustered into 16 clusters at each level, and then we continue like this, and we associate a memory for each of the clusters. For a given context, we compute the embedding, and we traverse this hierarchy to have a branch, and we attach this branch to our model to answer the query. The amount of retrieved memory is very small because it's only the retrieved branches, whereas the total memory is very large, exponentially grows with the depth of the hierarchy. How do we train this model? Training this network is again like quite straightforward. Given a context, we retrieve the associated memories and optimize the standard next token prediction loss. And one question is like, why does this architecture naturally separate knowledge and reasoning from each other? The reason is this: the anchor model parameters, as well as memories near the root of the hierarchy, are updated using examples from a wide range of contexts. As a result, they are incentivized to learn broadly applicable patterns, common sense knowledge, and reasoning abilities. Whereas memories deeper in the hierarchy are updated much less frequently and with much more specific context. Consequently, they specialize in storing long-tail knowledge. We designed an experiment to test this hypothesis. We asked the model to predict atomic numbers of elements in the periodic table. And in this graph, what you see is that the elements are sorted according to their frequency, and the blue curve shows that frequency. On the left, most common elements like oxygen, hydrogen, or carbon. What we observe is that the single monolithic model actually accuracy reduces very significantly as we look at rare elements, whereas when we append these memories to our model, we can have a pretty good accuracy across the board for all the elements. In the interest of time, there are a lot of design choices about how we use different kinds of memories and what kind of a hardware architecture this might imply. But in the interest of time, I'm going to skip this and come to the results. So in here, what we show is that we trained 3 different size models using these hierarchical memories and compared them with using no hierarchical memory or a slightly larger memory. And what we observe is that using a 160 million parameter model, for example, we can reach the accuracy of a 410 million parameter model using these memories. One other benefit of this is that we don't need to actually train these memories together with the model all the time. If we have a pre-trained model such as Gamma or Quan or Llama, we can just attach these models and then learn just the memory part of the things, and we can actually get still significant memories. In the interest of time, I'm moving a little bit fast, but please take a look at the paper that's been published in ICLR 26 about this method, that you will find a lot of different ablations and analysis. This concludes my talk. I would like to sincerely thank all my collaborators, without whom this work and presentation would not have been possible. All the papers that I have discussed in this talk are available in arXiv, and most of the code is actually available again on arXiv, on GitHub. We release our datasets in Apple's Hugging Face space, and you can download them there. We use a new framework called MLX for Apple Silicon, developed by Apple MLR, to benchmark our models on device. I would encourage actually using this framework, which is very powerful. And we have available positions for internships or full-time research. If you are interested in, please feel free to reach out to me. Thank you.